this. Okay, recording in progress. So we consider in this context our ontologies based on description logics. That means I'm, as a description logic researcher, have this view on OWL that I focus mostly as a standard for specifying description logic ontologies. And the problem we are concerned with is that developing, maintaining, and understanding ontologies can be challenging already due to the complexity. Many modern ontologies have large numbers of classes and axioms, and the interactions between the different axioms in an ontology can be complex. The good thing is that reasoning with description logics, and OWL in particular, is in a way explainable by design, because inferences are performed through symbolic reasoning. That means, in theory, we can explain anything that happens when we do reasoning with an ontology. Now, the vision that forms the context of this talk is that we would like to see ontology tools that support an ontology user the way a tutor would. That means they should explain inferences performed by a reasoner. They should thereby offer different types of explanations, and they should guide the user to a solution to their problems and help them understand the reasoning in general, to help them develop an intuition about what is happening with their ontology. To illustrate this vision a little bit, I show you here a screenshot of Protégé, a popular tool for developing OWL ontologies. Some of you might have worked with it already. And in Protégé, we can access different classes and find then a view for this class that includes both stated information stated by the user and information inferred by a reasoner. Now, a user might want to understand why something was inferred by the reasoner. So in Protégé, these inferred things are marked in yellow. And for example, the user would like to understand the mechanism of the ontology, to understand how things are actually derived. Or it could be that he sees something that looks surprising or incorrect, and he would like to understand whether there's actually a bug he needs to fix. So Protégé has some standard functionality. If you press on a question mark, you get a view like this. And what is shown here is a set of justifications. Justifications are a set of axioms, minimal sets of axioms from the ontology that are kind of responsible for the entailment, that are sufficient for creating this entailment inferred by the reasoner. Now, recently, we've developed a plugin for Protégé that is supposed to help a bit more with understanding these inferences by showing a proof. A proof shows smaller steps of reasoning leading from the axioms in the ontology to the conclusion the user would like to have explained. But what do we do if something is missing? Something that we would have expected the reasoner to derive was actually not derived. For example, you see here is a kind of a crippled version of the pizza ontology for illustration. We might have a definition of the concept for margarita pizza, and we might be surprised that it has not been classified as vegetarian pizza. In particular, a user that is practically oriented might want to understand how he can ensure that it gets correctly classified as vegetarian pizza. What is missing? Now, if we want to provide a detailed explanation for this particular case, then it is not sufficient to just look at the axioms that are in the ontology. We have to refer to information that is missing. And for this, we could use abduction. So what you see now is actually a new version of this plugin that we're currently developing, just to illustrate the idea. And what you do here is you enter axioms or DL axioms that you would have expected to be derived by the reasoner. And the tool should then tell you which axioms would be missing to create this entailment. Now, of course, a way to make margarita become classified as vegetarian pizza is just by stating this directly, but this is not really what we mean by an explanation. Just saying that margarita is vegetarian pizza is not really, it's not really what we want. Rather, we would like to find out which axioms should be added that actually talk about a margarita pizza to ensure that the reasoner can infer that it's a vegetarian pizza. And for that, we would then select terms that are somewhat related to a margarita pizza, and the tool should provide us with a set of axioms that use only these names and that are sufficient for creating this entailment. These axioms can then be added to the ontology, and we can also look at the proof to understand how this missing information would then be used to classify Margarita as a vegetarian pizza. So this type of reasoning is called abductive reasoning or abduction. And this is a term that was introduced in the late 19th century by Charles Sanders Peirce. The general idea can be formalized as follows. We assume that we have some knowledge K, and we have an observation phi, which is maybe a logical formula that does not follow from the knowledge itself. And now we would like to generate a good hypothesis H that, when added to the knowledge, should logically create an entailment of the observation. So the original idea of this is to find some form of formalization of what is a rational explanation for some observed phenomenon. The example that's often used is, let's say we observe that the street is wet, and a hypothesis for why the street is wet could be that it was raining, because with our knowledge of the world, we would infer from the fact that it was raining that the street is wet. But of course, it's not the only possible explanation, but it's a rational explanation. So note that so far I did not say what good means. That's going to come later. Now, abduction is put in contrast usually with deduction and induction as different types of logical reasoning. Deduction is what we are classically concerned with when talking about logic. Here we're given knowledge and we generate formulas or facts that logically follow from this knowledge. That's called deduction. In a way, abduction works in the other direction. It starts from the consequence and it moves towards possible antecedents or possible premises that would allow us to derive the observation. Another term usually mentioned in this context is induction, where we are not faced with one observation, but many observations, and we're trying to find a generalization of these observations to derive some general property. Now, this type of abduction has been considered for many logical formalisms in computer science pretty much since the early 90s. And for different logical formalisms like propositional logic, first-order logic, and of course description logics. And this original idea of using abduction to create like rational explanations can of course also be applied for description logics. So explaining missing entailments is one possible application. Finding rational explanations of unexpected observations would also be a possible application. So I'm not going to go into detail in this example. I just want to tell the idea. We could, for example, use a geological ontology with information about geology to generate hypotheses that explain some geological phenomenon that we have observed. Now, in the literature on abduction and description logics, we find different types based on the type of thing that we want to hypothesize and the type of observations. So early works, for instance, focus usually on concept abduction. Here, basically, the idea is to generate subsumees of a given concept. We have a concept and we would like to find a more general concept that entails this concept. So we're basically doing this backward reasoning on the level of the subsumption hierarchy. What we're concerned here when explaining missing entailments is more in the line of this, where we're actually generating axioms. And here one usually distinguishes between T-box, A-box, and knowledge-based abduction. T-box abduction means that the observation is a terminological information, like a subsumption between concepts, and we would like to generate terminological axioms. And similarly, A-box abduction deals with assertional facts, and knowledge-based abduction generalizes both. Now, the question is, of course, how to select a good hypothesis. So far, this was completely underspecified. And there's usually a set of conditions one poses on a logical level. So first, of course, it makes sense to require the hypothesis to be consistent with the knowledge. We don't want to derive any contradictory information. Also, when repairing an incomplete ontology or explaining why something is missing, we would not just want something that destroys the ontology by making it inconsistent. Another criterion that makes a lot of sense that is usually considered is some sort of minimality criterion. So we would like to have a hypothesis or an explanation that is as small as possible, that doesn't contain unnecessary axioms, that maybe contains a small number of axioms, or we might want it to be semantically minimal, by which we mean that it should be logically the weakest hypothesis that makes the least assumptions on a semantic level. Finally, we have properties like relevance and explanatoriness that kind of try to express that the hypothesis should really be used in combination with the knowledge to create the observation. And the aim of these conditions is kind of to give on a logical level conditions for a hypothesis to be well suited to a problem. However, I claim that any type of specification of what makes a good hypothesis that works purely on the logical level alone cannot be sufficient. And that I want to illustrate with an example. So let's say we have some sort of medical ontology. This is a highly simplified example, of course. And we would like to explain an observation of the form P1 is a corona patient. We would like to know possible causes or find an explanation for this. Now, if we look at this purely logically, we could say that, say, the ontology contains a definition of a corona patient as a patient that is infected with corona. Well, then we could logically say, okay, P1 is a patient that has corona. But that doesn't really explain anything or add anything. It's just kind of reformulating what we started with. However, we could consider a very similar setting with just the names exchanged. This is the same structure, the whole thing. We only changed the names. And here we would like to find a hypothesis for why the computer C1 is infected. In the context where this is executed, infected computers are exactly those that are vulnerable and have been in contact with a computer worm. And now the explanation that uses this equivalence would actually be somewhat explanatory. We would say the computer is infected because it was vulnerable and in contact with a worm. So what this kind of illustrates, even though it's a highly simplified example, is that the logical structure of the knowledge and the problem cannot be sufficient to determine what is a good hypothesis. Rather, we need further knowledge from the user. And there's different ways to restrict the solution space with the aim of getting more useful explanations. A typical approach is to specify a set of so-called abusable axioms or concepts. For example, we would here list different axioms that we would like to see in the solution. And now the requirement is that every hypothesis that we generate should use only axioms from the set. Of course, if we want to explain missing entailments, this is a bit weird because we kind of have to know beforehand what axioms we're looking for. So it might not be so useful for this case. Another approach is to instead specify a signature for the hypothesis. Here by signature, I mean names or terms that can be used in an explanation, the vocabulary. And the requirement is now that the hypothesis should use only names from the signature. So in the literature, this is often used in combination with other constraints on the structure of the axioms that occur in a hypothesis. For example, we might disallow complex concepts or specify syntactic patterns on the shape of the axioms. But again, then the user has to kind of know what he's looking for. So more useful, it could be to just allow arbitrary concepts that are used with the names within the vocabulary what is given, but otherwise can be connected in an arbitrary ways. This gives, of course, more flexibility and might lead to better results. But the downside is that then the solution space becomes unbounded, because when we can build arbitrary expressions with the vocabulary handed over, we can also build arbitrary complex and large expressions. So this is in fact what we've seen in the example, and what we are currently implementing in the plugin is exactly this type of abduction, where names can be combined in an arbitrary fashion that doesn't have to be specified by the user. We believe that in many application scenarios, the signature will be quite natural, but in any case, our plugin will support the user in finding an appropriate signature, for instance, by starting with the names that are in the observation and excluding them, and by allowing the user to easily select terms that shouldn't be there. The problem is this also comes at a price. So we analyzed the theoretical complexity of abduction. So how hard is it to perform this type of abduction, and how large can solutions get? So we looked here at different description logics that could be used to formalize the ontology, starting from lightweight logics to more expressive ones. And we considered here the additional constraint that the hypothesis should be consistent with the knowledge. And it turns out, even if we consider A-box abduction and we do not consider complex concepts, we only consider maybe the introduction of anonymous individuals, the problem becomes very hard to undecidable already in moderately expressive description logics. And the hypotheses can in fact be very large. This gets even worse when we allow the use of complex expressions. As I said, the size here becomes unbounded. We can nest expressions as much as we want in description logics. And now the problem of deciding whether there is a hypothesis that is consistent to the knowledge and within the signature becomes very difficult, and the hypothesis can become huge. So what this means is, if n is the size of my ontology and the observation that I would like to explain, then it can be that the only hypothesis that does that is triple exponentially large in comparison to the input. So this is really gigantic. So, but on the other hand, we're kind of used to that. In the OWL world and in the description logic world, complexities are always very high, and that usually doesn't scare us off with building large ontologies and using expressive logics. And of course, what we've seen, there is an implementation that we implemented 2 years ago. And the idea here is to reduce abduction to deduction. So this is an approach for knowledge-based abduction that works to derive facts or terminological knowledge in the description logic ALC. We also generate complex concepts here. We do not invent names. We only consider the signature that is given. And the idea is to add the negation of the observation to the knowledge and translate it to a normalized form. And now we perform inferences on all the names that are not in our target signature. We eliminate the names that shouldn't be in our hypothesis. This way we get a new normalized ontology that we can then translate back to get a hypothesis. Now, some tricks are used to make this practical and to make it work in practice and to ensure that it always terminates. And what comes out of this method is actually not the final hypothesis, but it is a kind of formula that may look like this, that uses additional operators that are usually not part of a description logic. So we might have a disjunction of different, to have different alternative explanations. And we may use this strange operator here, which is a fixed point operator. The reason simply be that there might be infinitely many solutions, and we would like to capture the entire solution space. This is somewhat related to semantic minimality, but it is in a way more powerful because we don't want just any semantic minimal solution. We would like to find all of them. Now, from this formula, we can generate hypotheses in a classical description logic that can be represented in OWL by using unraveling. And this is actually what we implement also in this plugin. So what we can see in this case, if there are some cyclic relations that are relevant to the missing entailment to be explained, then this will be shown as a long list of more and more nested expressions being generated. And with the intuition that the user gets an idea on what is the underlying principle. So the complexity that I showed look very high. The question is, does this act, how does it perform in practice? And I think it performs all right. So we tested this on real ontologies. We generated the abduction problems otherwise, observations and signatures, because there wasn't really a benchmark. And we applied our method for computing these formulas that capture the hypotheses to the abduction problems. And we find computation times that are usually in the range of seconds and explanations of moderate size. Of course, this is done with artificial examples. Now that we have the plugin, we plan to test it also on more realistic examples. Yeah, and with that, I think my time is almost up and I come to the conclusion. So I told you a little bit about abduction and on motivating it for explaining missing entailments. The idea of abduction is to generate an extension of the knowledge that you have that would create a given entailment to make sure that something is entailed. And I argue that usually one needs a criteria to select good hypotheses, such as consistency, minimality, or signature restrictions. There are many more that I didn't cover in this talk. And I focused then a little bit on signature restriction, showing that this problem can be challenging, but it's often possible in practice. And I also illustrated a little bit our vision on how this should be used in the end by showing the coming version of our plugin for Protégé, where this is implemented. What I did not discuss here is that there will be also other ways of explaining missing entailments, for example, by generating models or a different type of abduction that I did not discuss here. And since we're talking about explainability, there's also another tool that you might want to check out that comes from this family of explaining DL reasoning. Future directions, I think my time is up, just give me a few minutes. So my colleagues currently are conducting a user study to get an impression on, what is that? Okay, I don't know what happened.
No, yeah, everything is okay, yeah. You're still
I just got the message that this is being recorded, but okay, so we're currently conducting a user study to understand how abduction compares with other methods of explaining missing entailments. And of course, signature restrictions are one way. There's many different ways of restricting the search space, of guiding towards good hypotheses to explain why something cannot be inferred, that we're currently investigating. And we are also developing other methods for abduction, of course. Yeah, and that's the end of my talk. Thank you very much.
Thank you so much. So you stop the recording.